The unexpected hanging paradox. A judge tells a prisoner, "You will be executed next week on one weekday, but the execution will be a surprise. You will not know the day of the execution until the executioner comes for you." The prisoner begins to reason through the statement. He first rules out Friday because if he is still alive by Thursday night, Friday will be the only day left, and therefore it could not be a surprise. If Friday is impossible, then Thursday also becomes impossible, because if he is alive on Wednesday night, with Friday already ruled out, Thursday would be the only possible day left, making it predictable. Following the same reasoning, Wednesday, Tuesday, and Monday are each eliminated in turn. His conclusion is that there is no day left on which the execution can occur without breaking the promise of surprise, so it cannot happen at all. Yet when Monday arrives, the executioner appears, and the prisoner is completely caught off guard. The execution is both on a weekday and unexpected, exactly as the judge declared. The paradox emerges because the prisoner's step-by-step logic, while seemingly airtight, ignores a subtle flaw. His entire chain of reasoning assumes that his predictions will remain correct in real time, but the act of predicting changes how the situation plays out. The surprise is possible precisely because he convinces himself that it is impossible. This paradox challenges the very nature of self-referential reasoning, where predictions about the future can disrupt the future itself. It has echoes far beyond this story. In economics, when a financial collapse is predicted with certainty, people's actions to avoid it can prevent it entirely, erasing the conditions that made it likely. In politics, when a revolution is expected on a specific date, authorities can prepare and stop it, meaning revolutions often succeed only when least anticipated. Even in everyday life, routine inspections, security checks, or surprise tests work best when their timing defies prediction. The unexpected hanging paradox forces us to confront an uncomfortable truth. Sometimes, the most effective way to ensure that something happens is to make people believe it will not, and the most effective way to guarantee a surprise is to allow overconfidence to blind us to its possibility. It is a reminder that in certain systems, the very act of thinking about an outcome becomes part of the system itself, and logic can be turned upside down by the simple fact that we are trying to use it.
The Grandfather Paradox. If you could travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But if you were never born, you couldn't have traveled back in time to prevent their meeting in the first place. This creates an impossible loop where the cause prevents its own existence. The Grandfather Paradox cuts to the heart of our understanding of causality and time itself. It's not just a science fiction curiosity, but a genuine problem that physicists grapple with when considering the theoretical possibility of time travel. The paradox reveals fundamental questions about how cause and effect work in our universe. Consider the logical structure here. Every event in this scenario both must happen and cannot happen. Your grandfather must meet your grandmother because you exist to travel back in time, but your grandfather cannot meet your grandmother because you prevent it. This isn't just a contradiction, it's a contradiction that creates itself. Some scientists have proposed solutions. The many worlds interpretation suggests that traveling back creates a new timeline, a parallel universe where your grandparents never meet, while you continue to exist in your original timeline. But this solution raises its own questions. If you create a new timeline, are you really changing the past, or just creating an alternate present?
Another proposed solution is the Novikov self-consistency principle, which argues that the universe somehow prevents paradoxes from occurring. In this view, if you tried to prevent your grandparents from meeting, something would always go wrong with your plan. You might miss your flight, Your time machine might malfunction, or events would conspire to ensure your grandparents meet despite your efforts. But perhaps the most unsettling possibility is that the paradox reveals something fundamental about the nature of time itself. Maybe time travel to the past is simply impossible, not because of technological limitations, but because it would create logical contradictions that the universe cannot tolerate. The grandfather paradox might be telling us that causality is more rigid than we imagine. The paradox also raises questions about identity and existence. If you prevent your own birth, do you cease to exist gradually or instantly? Do you remember your original timeline, or do those memories fade as reality reshapes itself around your absence? These questions push us to consider what it really means to exist and how our identity is tied to the sequence of events that brought us into being. Modern physics doesn't rule out time travel entirely. Einstein's theory of relativity shows that time is relative and can be dilated. Theoretical constructs like wormholes or closed time-like curves could potentially allow travel to the past. But every time physicists work through the mathematics, they encounter versions of the grandfather paradox that suggest the universe has built-in protections against causal violations.
The two envelopes paradox. You are presented with two identical envelopes. You are told that one contains exactly twice as much money as the other, but you have no idea which is which. You are invited to choose one envelope at random and keep whatever is inside. After making your choice, but before opening it, you are given the option to switch. At first, this might seem like a simple coin flip of a decision, but then the reasoning begins to spiral. Suppose the envelope you picked contains an amount X. That means the other envelope must contain either X/2 or 2X. You might think there's a 50% chance of gaining X if you switch, and a 50% chance of losing only X/2. On paper, this makes the expected value of switching appear greater than the value of keeping your envelope. So logically, it seems you should switch. But then something strange happens. If that logic is correct, then no matter which envelope you pick at the start, you should always switch, because the calculation will look the same from either side. And if switching is always better, you could, in theory, switch forever, never opening an envelope at all. The paradox traps you in an infinite loop of indecision, as if your mind is caught between two equally convincing arguments that cancel each other out. The flaw lies deep in the assumptions. When you label the amount in your chosen envelope as X, you treat it as if it could equally be the larger or smaller sum. But in reality, the actual amounts are fixed from the start and do not shift depending on your choice. The X in your reasoning is not a stable point. It shifts its meaning depending on which envelope you imagine it to be. This misalignment creates a statistical illusion, making the math suggest you will gain by switching, when in fact there's no real advantage. What makes the two envelopes paradox so unsettling is how persuasive it feels at first. Your intuition tells you switching is smart. Your calculations seem to confirm it, and yet the conclusion leads to absurdity. The more you think about it, the more you feel that something is off, but pinning down exactly where the reasoning goes wrong is difficult. It's a trap born from our instinct to compare what we have with what we might gain. An instinct that usually serves us well, but here creates a loop with no escape. In the end, the paradox is less about envelopes and money, and more about the limits of our reasoning under uncertainty. It shows how a tiny flaw in the way we frame a problem can create a convincing argument for an impossible action, and how even simple scenarios can challenge our most basic sense of logic.
The twin paradox.
It comes from Einstein's theory of relativity, and it's one of the best examples of how time doesn't always work the way we expect. It starts with a strange but clear question. If two people are born at the same time, can one of them end up younger than the other without any tricks or special effects, just because they moved differently through space? According to relativity, the answer is yes. Here's how it works. Imagine two twins. They are exactly the same age at the start. One stays on Earth, living a normal life. The other gets into a spaceship and travels far into space at a speed close to the speed of light. In everyday life, we think of time as something steady. A second is a second for everyone. But relativity says that the faster you move, the slower time passes for you compared to someone who isn't moving as fast. This effect is called time dilation. From the point of view of the twin on Earth, the space traveler's clock is running slower. If the trip lasts many years on Earth, much less time passes for the traveler. When the space twin finally comes back, they find that their sibling on Earth has aged more. For example, maybe 10 years have passed for the Earth twin, but only 6 for the one who traveled. At first, this seems simple, until you look at it from the traveler's perspective. If motion is relative, the traveler could just as easily say, "I wasn't moving, Earth was moving away from me." If that's true, then from their point of view, time should have been slower for the Earth twin. Both can't be younger than the other when they meet. That's the paradox.
The reason this doesn't create a contradiction is that the situation isn't perfectly equal. The twin in the spaceship has to accelerate to leave Earth, turn around in deep space, and then decelerate to return. Each of those changes in speed puts them in a different frame of reference, a way of measuring space and time. The twin on Earth stays in the same frame of reference the whole time. That's what breaks the symmetry and makes the space traveler the younger one when they reunite. This isn't just theory. Scientists have tested time dilation using extremely precise atomic clocks. When one clock is flown around the world on a jet and then compared to a clock that stayed on the ground, the traveling clock is behind. It has experienced slightly less time. Astronauts on the International Space Station also age more slowly than people on Earth, but the effect is tiny because they're not traveling anywhere near light speed. The twin paradox shows that time isn't universal. It doesn't flow the same for everyone. It's linked to movement and gravity, and it can stretch or shrink depending on where you are and how you move. That's hard to accept at first because our daily lives don't give us any reason to think time works that way. But in the universe, on scales of huge distances and high speeds, time behaves in ways that go far beyond our everyday experience.
The lottery paradox. Imagine a lottery with 1 million tickets, only one of which will win. From the perspective of any single ticket, the odds are overwhelmingly against it winning, 999,999 to 1. Given that, it seems perfectly reasonable, even rational, to believe of each individual ticket that it will lose. After all, the chance of winning is so minuscule that treating it as a certainty to lose feels like sound judgment. However, the paradox emerges when you consider all the tickets together. Since one ticket must win, believing that every single ticket will lose is a contradiction.
You end up in a situation where your rational beliefs about individual tickets, taken collectively, lead to a logical impossibility. How can you rationally believe each ticket will lose, but also accept that at least one ticket will win? This clash exposes a fundamental tension between probabilistic reasoning and logical consistency. The lottery paradox forces us to reconsider what it means to hold a belief rationally. Traditionally, we think beliefs should be internally consistent and based on evidence. But here, what seems justified on a micro level, believing a ticket will lose, results in an impossible macro-level belief when extended to all tickets. This paradox suggests that our intuitions about probability and rationality do not always fit neatly together. Philosophers have approached this paradox from various angles. Some argue that rational belief should be replaced with degrees of belief or confidence, known as credences, rather than all-or-nothing beliefs. In this view, it is reasonable to have high confidence that a ticket will lose without fully believing it. Others suggest that the paradox exposes a flaw in how we aggregate individual beliefs into a collective one. Still others see it as a warning about the limits of human reasoning in situations involving large numbers and uncertainty. Beyond the lottery example, this paradox has wide implications. It challenges how we assess risk, make decisions under uncertainty, and manage evidence in fields like science, law, and everyday life. It reminds us that certainty is rare and often illusory, and that sometimes we must accept ambiguity in our beliefs. The lottery paradox ultimately shines a light on the complexities of knowledge and belief. It teaches us that what seems rational in isolation may not hold up when viewed as part of a larger system, and it encourages a humble approach to what we claim to know, especially when dealing with the uncertain and the unpredictable.
The Paradox of Achilles and the Tortoise. In this paradox, Achilles, a swift runner, races a tortoise that has a head start. The tortoise moves slowly, but because it started ahead, Achilles must first reach the point where the tortoise began. However, by the time Achilles reaches that point, the tortoise has moved forward a little. Then, Achilles must reach this new position. Each time Achilles reaches where the tortoise was, the tortoise has advanced further. This process repeats infinitely, suggesting that Achilles can never catch up. At first, this reasoning seems logical, dividing the race into an infinite number of smaller steps. But it also leads to an impossible conclusion, that motion itself is an illusion, because Achilles can't overtake the slower tortoise despite running faster. The paradox challenges the way we think about continuity, infinite sequences, and how we measure space and time. Modern mathematics, with the concept of converging infinite series, resolves this paradox by showing that the sum of infinitely many decreasing distances can be finite. Achilles will catch up in a finite amount of time, despite the infinite number of steps. But Zeno's paradox remains a powerful reminder of the difficulties in reconciling intuitive ideas about motion with the infinite. The paradox pushes us to think deeply about how reality works at a fundamental level. It highlights that concepts like infinity and continuity are more subtle than they appear, and that the way we describe the world through logic and mathematics can challenge our everyday experience. The story of Achilles and the tortoise endures because it forces us to confront how something as simple as a race can reveal profound puzzles about time, space, and change.
The Paradox of the Heap. If you have a heap of sand and remove one grain, you still have a heap. Remove another grain, still a heap. Keep removing grains, one by one. At what exact point does it stop being a heap? If removing one grain never transforms a heap into a non-heap, then even a single grain should be a heap, which seems absurd. This ancient paradox, also known as the Sorites paradox, exposes fundamental problems with how we categorize the world. It shows that many of our most basic concepts are surprisingly difficult to define precisely. The word heap feels clear and meaningful until you try to determine its exact boundaries. The paradox applies to countless aspects of human experience. When does a child become an adult? When does day become night? When does a hill become a mountain? When does a group of people become a crowd? These questions seem to have obvious answers until you try to pinpoint the exact moment of transition. The problem isn't just semantic. It reflects a deeper tension between our need for clear categories and the continuous nature of reality. The world presents us with gradual changes and smooth transitions, but our language and thinking rely on discrete categories with sharp boundaries. We need words like tall, old, expensive, and intelligent, but none of these concepts have precise cutoff points. Consider the legal implications. Laws often depend on clear definitions and bright-line rules. A person is either a minor or an adult, either guilty or innocent, either sane or insane. But the underlying realities these categories attempt to capture are often matters of degree. How do legal systems handle this fundamental mismatch between categorical thinking and graduated reality?
Philosophers have proposed various solutions to the heap paradox. One approach argues that concepts like heap are inherently vague, and that vagueness is a legitimate feature of language. In this view, there's no precise point where a heap becomes a non-heap, because the concept itself is imprecise. The boundaries are genuinely fuzzy, not just hard to detect. Another solution involves degrees of truth. Instead of something being simply true or false, it can be partially true. A collection of 10,000 grains is definitely a heap. A single grain definitely isn't. And collections in between have varying degrees of heapness. This approach preserves our intuitive understanding while acknowledging the gradual nature of the transition. The supervaluationist approach tries to preserve classical logic by arguing that statements about borderline cases lack definite truth values. They're neither true nor false, but indeterminate. This maintains logical consistency while acknowledging the reality of vague concepts. Modern cognitive science suggests that this paradox reflects how human categorization actually works. We don't typically categorize things by checking them against precise definitions. Instead, we use prototype-based thinking, comparing new examples to typical cases of a category. A heap is more like a typical heap or less like one, but there's no sharp boundary where heapness suddenly appears or disappears. The paradox also connects to deeper questions in mathematics and logic. Set theory, which underlies much of modern mathematics, relies on the idea that objects either belong to a set or they don't. But if concepts like heap are fundamentally vague, how can we create mathematical systems that depend on precise membership criteria? Some mathematicians have developed fuzzy logic and fuzzy set theory to handle these situations. But the fundamental tension remains.
The Ship of Theseus. The ancient Ship of Theseus is preserved in a harbor, but over the years its wooden parts begin to rot. The caretakers replace each rotting plank with an identical new one. Eventually, every single original piece has been replaced. Is this still the same ship? Now imagine someone collected all the original rotting pieces and rebuilt the ship using only those parts. Which ship is the real Ship of Theseus? This paradox has puzzled philosophers for over 2 millennia because it strikes at the heart of identity and continuity. What makes something the thing it is? Is it the physical materials, the structure, the history, or something else entirely? The question becomes even more complex when we consider that both ships have equally valid claims to being the real Ship of Theseus. The paradox isn't just about ancient ships. It applies to every object and even every person. Your body replaces most of its cells over a period of about 7 years. The atoms that make up your body today are almost entirely different from the atoms that made up your body a decade ago. Yet you feel like the same person. What maintains your continuity of identity through this constant physical change? Consider a modern version of the paradox. Your car needs repairs, and over several years you replace the engine, the transmission, the body panels, the interior, and every other component. Nothing original remains. Is it still your car, or have you gradually purchased a different vehicle? If someone had collected all your discarded original parts and rebuilt a car from them, which car would have the stronger claim to being your original vehicle? The paradox becomes even more interesting when we consider gradual versus sudden replacement. If the ship's parts were replaced one at a time over many years, we're inclined to say it's the same ship. But if all the parts were replaced simultaneously, we might feel it's a different ship made from the same materials. This suggests that the process of change, not just the end result, affects our judgment about identity. Different philosophical traditions have proposed various solutions. The materialist view holds that identity is tied to physical substance. In this view, the ship built from original materials would be the true Ship of Theseus, regardless of its history of disassembly and reconstruction. Physical continuity takes precedence over functional continuity. The functionalist approach argues that what matters is continuity of form and function. The ship that maintained its shape and purpose through gradual replacement would be the real one, because it preserved the essential characteristics that make it a ship. The pattern and organization matter more than the specific materials. Some philosophers embrace the idea that both ships, or neither ship, could be the true Ship of Theseus. This might seem like avoiding the question, but it reflects a deeper insight that identity might not be as binary as we assume. Perhaps identity exists on a spectrum, with both ships having legitimate but partial claims to being the original. The paradox becomes particularly relevant in discussions of personal identity and consciousness. If your brain were gradually replaced neuron by neuron with functionally identical artificial neurons, at what point, if any, would you stop being you? Would the process matter if it happened all at once versus gradually? Would you be the same person if your consciousness could be uploaded to a computer and your original brain destroyed? Modern technology makes these questions more than philosophical curiosities. We can transplant organs, replace limbs with prosthetics, and even envision replacing biological parts with mechanical ones. As these technologies advance, the Ship of Theseus paradox will become increasingly relevant to practical questions about human identity and rights. The paradox also raises questions about ownership and authenticity. If you own the Ship of Theseus, and it's gradually replaced, do you still own the same ship, or have you acquired a different one? Museums face similar questions when they restore artifacts. If a painting is extensively restored, with most of the original paint replaced, is it still the same artwork the artist created? Zeno's paradoxes. To reach a destination, you must first travel half the distance. But before you can travel half the distance, you must travel a quarter of the distance. Before that, an eighth, then a 16th, and so on. Since there are infinite divisions to make, it seems you can never actually start moving. Yet, obviously, people move all the time. Zeno of Elea created several such paradoxes around 450 BCE, and they continue to challenge our understanding of motion, space, and infinity. The paradoxes seem to prove that motion is impossible, despite the obvious fact that motion occurs constantly. This contradiction between mathematical reasoning and physical reality has puzzled thinkers for over 2 millennia. The race between Achilles and a tortoise presents another version. If the tortoise gets a head start, Achilles must first reach the point where the tortoise began. But during the time it takes Achilles to reach that point, the tortoise has moved farther ahead. When Achilles reaches the tortoise's new position, the tortoise has moved again. This process continues infinitely, suggesting that Achilles can never overtake the tortoise, despite being faster. The arrow paradox takes a different approach. At any instant in time, a flying arrow occupies a specific position and is therefore motionless at that instant. Since time consists of instants and the arrow is motionless at every instant, the arrow never moves. Yet, arrows clearly do move when shot from bows. These paradoxes expose deep problems with how we think about continuous motion, infinite division, and the nature of space and time. They suggest that either motion is impossible or our mathematical understanding of space and time is fundamentally flawed. Since motion obviously occurs, something must be wrong with the reasoning, but identifying the error proves surprisingly difficult. Modern mathematics resolves some aspects of Zeno's paradoxes through the concept of limits and convergent infinite series. The infinite sequence of distances in the first paradox adds up to a finite total. Half plus a quarter plus an eighth plus a 16th continues infinitely, but the sum converges to exactly 1. Mathematical techniques developed in the 17th and 18th centuries show that infinite processes can have finite results. However, the mathematical resolution doesn't fully satisfy everyone. Convergent series solve the arithmetic problem, but questions remain about whether mathematical solutions address the conceptual issues Zeno raised. Does the mathematical fact that infinite series can converge explain how actual physical motion works, or does it merely describe motion without explaining its possibility?
The paradoxes also raise questions about the nature of space and time themselves. If space is infinitely divisible, as the paradoxes assume, then every finite distance contains infinite points. But if space consists of discrete, indivisible units, then the paradoxes disappear. Some modern theories in physics, such as loop quantum gravity, propose that space might indeed be quantized at the smallest scales. Zeno's paradoxes anticipated issues that remain relevant in contemporary physics. Quantum mechanics suggests that motion at microscopic scales doesn't follow the smooth, continuous paths that classical physics assumes. Particles don't have definite positions and velocities simultaneously, and they can tunnel through barriers or appear to jump between locations without traversing the space between. The arrow paradox touches on fundamental questions about time. If time consists of discrete moments, then motion becomes a series of static snapshots, making it unclear how change occurs. If time is continuous, then the notion of an instant becomes problematic. How can we define motion at a specific instant if instants have no duration? Some philosophers interpret Zeno's paradoxes not as arguments against motion, but as demonstrations that our common-sense understanding of motion is inadequate. They might be showing us that motion is more mysterious and complex than we typically realize, requiring sophisticated mathematical and physical concepts to understand properly. The paradoxes also illustrate how infinity creates conceptual problems. Human intuition evolved to deal with finite quantities and processes. When we encounter infinite sequences or infinitely divisible spaces, our intuitions often mislead us. Zeno's paradoxes might be showing us the limits of intuitive reasoning when confronting infinite processes. Modern physics has revealed that both space and time might be quantized at the Planck scale, the smallest meaningful units in the universe. If this is correct, then Zeno's assumption of infinite divisibility is physically incorrect. Space and time might consist of discrete units so small that infinite division isn't actually possible. Nevertheless, even if space and time are quantized, Zeno's paradoxes remain valuable for understanding the relationship between mathematical models and physical reality. They remind us that logical reasoning, even when seemingly airtight, must be checked against observation and experience. They also demonstrate how ancient philosophical problems can illuminate modern scientific questions about the fundamental nature of reality.
The paradox of free will. If the universe is deterministic, where every event is caused by previous events according to natural laws, then all your choices are the inevitable result of prior causes. You couldn't have chosen differently than you did. But if the universe includes genuine randomness, then your choices are influenced by random events beyond your control. Either way, it seems you don't truly have free will, yet you experience making choices every day. This paradox cuts to the core of human experience and responsibility. We feel like we make genuine choices, deliberating between options and selecting actions based on our reasons and values. Yet, modern science suggests that everything, including human behavior, follows from prior causes according to natural laws. This creates a tension between our subjective experience of freedom and the objective picture of causal determination. The deterministic side of the dilemma seems powerful. If your brain is made of particles following the laws of physics, then your thoughts and decisions are the result of physical processes. Those processes are themselves the result of earlier physical processes, extending back through your personal history to events before you were born. In this view, your sense of choosing is an illusion created by your limited awareness of the causal chains determining your behavior. Consider a specific decision, like choosing chocolate over vanilla ice cream. Your choice feels free and deliberate, based on your taste preferences and current mood. But those preferences developed through past experiences of eating different flavors.
Your current mood results from recent events, your brain chemistry, and countless other factors. Each of these factors has its own causal history. Traced back far enough, your choice seems to be the inevitable result of events beyond your control.
But introducing randomness doesn't seem to help. If quantum mechanics introduces genuine randomness into brain processes, your decisions might not be fully determined by prior causes. However, random events are by definition beyond your control. A choice influenced by random quantum events seems no more free than a choice determined by prior causes. Neither determination nor randomness appears to leave room for the kind of control that free will seems to require. Some philosophers embrace hard determinism, arguing that free will is indeed an illusion. In this view, we act according to our desires and beliefs, but those mental states are themselves the products of forces beyond our control. We can't choose our genes, our upbringing, or the experiences that shape our character. Since we don't control the ultimate sources of our actions, we're not truly responsible for them. Others adopt hard incompatibilism, arguing that free will is impossible, regardless of whether the universe is deterministic or indeterministic. Even if our choices aren't fully determined by prior causes, introducing randomness doesn't give us the kind of control that moral responsibility requires. True free will would require some impossible form of self-creation, where we somehow cause our own fundamental character and values. Compatibilist philosophers argue that free will and determinism can coexist. They redefine free will not as the absence of causation, but as acting according to your own desires and rational reflection without external coercion. In this view, a choice can be both free and determined as long as it flows from your own values and reasoning processes, even if those processes are themselves the result of prior causes. The consequence argument challenges compatibilism by pointing out that you're not responsible for the distant past or the laws of nature. Since your present actions are consequences of the past and natural laws, and you're not responsible for those, you can't be responsible for your present actions either. Compatibilists respond by arguing that this reasoning conflates different senses of responsibility and control.
Libertarian theories of free will propose that humans possess a special form of agency that isn't reducible to physical causation. These theories often invoke quantum indeterminacy or emergent properties of complex systems to create space for genuine choice. Critics argue that these theories either reintroduce the randomness problem or posit mysterious forms of causation not supported by science. The paradox has practical implications for moral responsibility and criminal justice. If people don't truly choose their actions, should we hold them responsible for crimes? Should punishment focus on deterrence and rehabilitation rather than retribution? These questions affect how societies structure their legal and ethical systems. Recent neuroscience research has intensified the debate. Studies show that brain activity associated with decisions can be detected before people report becoming aware of their choice. This suggests that conscious will might come after the brain has already committed to an action, rather than causing it. Critics argue that these experiments don't capture the complexity of real-world decision-making. Some philosophers propose that the free will debate rests on conceptual confusions. Perhaps our folk psychological notion of free will doesn't correspond to anything coherent that could exist in the natural world. Rather than asking whether we have free will,
we might need to develop new concepts that better capture the nature of human agency and responsibility. The paradox also intersects with questions about consciousness and personal identity. If free will is an illusion, what does this say about the nature of the self that supposedly exercises that will? Some philosophers argue that both free will and the unified self are useful fictions that don't correspond to objective reality. Despite the philosophical challenges, most people continue to experience themselves as free agents, making genuine choices. This disconnect between philosophical arguments and lived experience suggests that the paradox might reveal fundamental limitations in how abstract reasoning relates to embodied existence. Perhaps the question isn't whether we have free will, but how to understand the kind of agency we actually possess.
Fermi's paradox. The universe is vast and ancient, containing billions of galaxies with trillions of stars, many hosting planets that could support life. Given the enormous number of potential habitable worlds and the age of the universe, intelligent civilizations should have had plenty of time and opportunity to develop and spread across the galaxy. Yet, we see no evidence of alien civilizations anywhere. Where is everybody? This paradox, named after physicist Enrico Fermi, who first articulated it in 1950, represents one of the most profound puzzles in science. The numbers seem overwhelming. Our galaxy alone contains roughly 400 billion stars, and current estimates suggest that a significant fraction host planets in the habitable zone where liquid water could exist. Even if intelligent life is extremely rare, the sheer scale of the universe suggests it should have emerged many times over. Consider the timeline. The universe is approximately 13.8 billion years old, and our galaxy formed about 13.6 billion years ago. Earth is only 4.5 billion years old, which means there were billions of years before our planet even existed for other civilizations to develop. If any of these earlier civilizations had developed space travel and decided to expand across the galaxy, they would have had enormous amounts of time to do so. The math makes the silence even more puzzling. Even with relatively slow interstellar travel, taking thousands of years to journey between stars, a civilization could colonize the entire galaxy in just a few million years. This is a tiny fraction of the galaxy's age. If expansionist civilizations had emerged anywhere in our galaxy's history, their descendants or artifacts should be everywhere by now, including in our solar system. Various solutions to the paradox have been proposed, each with disturbing implications. The Great Filter hypothesis suggests there's some extremely difficult evolutionary step that prevents most life from reaching interstellar capabilities. This filter could be behind us, meaning we're among the rare species to pass through it, or ahead of us, implying that civilizations typically destroy themselves before achieving galactic presence.
If the filter is behind us, it might be the emergence of life itself, the development of complex cells, the evolution of intelligence, or the development of technology. Each of these steps might be so improbable that we're effectively alone in the galaxy. This would make us incredibly special, but also cosmically isolated. More troubling is the possibility that the filter lies ahead of us. Perhaps civilizations inevitably destroy themselves through war, environmental collapse, or technological disasters before they can expand beyond their home systems. The silence might be a graveyard of failed civilizations, each having reached our level of development only to face extinction.
The zoo hypothesis proposes that advanced civilizations are aware of us but deliberately avoid contact, perhaps preserving us in a kind of cosmic nature preserve. This explanation requires that all advanced civilizations agree to this policy, which seems unlikely given the diversity of motivations and values we might expect from different species. Another possibility is that we're looking for the wrong signs. Perhaps advanced civilizations don't expand physically across the galaxy, but instead focus on virtual worlds, microscopic engineering, or forms of existence we can't imagine. They might be all around us, but operating on scales or using technologies we don't recognize. The simulation hypothesis adds another layer to the paradox. If advanced civilizations create detailed simulations of their evolutionary history, there might be far more simulated beings than real ones. We might be simulated creatures in a digital universe created by beings we're trying to detect. This would explain why we don't see evidence of our creators. They exist outside the simulation. Timing might also explain the paradox. Perhaps we're among the first intelligent civilizations to emerge. The universe needed time to create the heavy elements necessary for rocky planets and complex chemistry. Earlier generations of stars lacked the materials for Earth-like worlds. We might be part of the first wave of intelligence in cosmic history.
The rare Earth hypothesis argues that while simple life might be common, the specific conditions required for complex life and intelligence are extraordinarily rare. Earth's location in the galaxy, its large moon, its magnetic field, its plate tectonics, and countless other factors might be necessary for the evolution of intelligence. If so, we might be alone not because life is impossible elsewhere, but because the requirements are so specific. Recent discoveries have both intensified and potentially resolved aspects of the paradox. We've found thousands of exoplanets, many in habitable zones, confirming that the raw materials for life are common. However, we've also learned more about the requirements for habitability, including factors like stellar activity, atmospheric retention, and magnetic fields that might be rarer than initially thought. The search for extraterrestrial intelligence continues to scan the cosmos for artificial signals, but the silence persists. Each year that passes without detection makes the paradox more acute. Either we're using the wrong methods, looking in the wrong places, or the universe is far emptier of intelligence than we expect. Some researchers propose that the paradox itself might be based on flawed assumptions. Perhaps intelligence doesn't naturally lead to expansion and communication. Maybe advanced civilizations turn inward, focusing on internal development rather than external exploration. Or perhaps they communicate using methods we haven't discovered or considered. The implications of Fermi's paradox extend beyond astronomy, to philosophy and human survival. If the great filter lies ahead of us, understanding it might be crucial for our species' survival. If we're alone, it emphasizes both our cosmic significance and our responsibility as potentially the only intelligence in our galaxy.
The paradox of choice. Having more options should make us happier and more satisfied with our decisions, but psychological research shows the opposite. When faced with too many choices, people become overwhelmed, make worse decisions, and feel less satisfied with what they choose. The freedom that options provide can become a burden rather than a benefit. This paradox challenges fundamental assumptions about human psychology and the benefits of freedom. Western culture generally celebrates choice as inherently valuable.
We assume that more options lead to better outcomes and greater satisfaction. Consumer culture is built on this assumption, offering endless varieties of products and services. Political systems emphasize the importance of choice in voting, career paths, and lifestyle decisions. However, research by psychologist Barry Schwartz and others has demonstrated that the relationship between choice and satisfaction is more complex. In studies involving everything from jam purchases to retirement plan selections, people with fewer options often make decisions more quickly and feel more satisfied with the results than those facing many alternatives. Consider the experience of choosing breakfast cereal at a modern grocery store. Dozens of brands offer hundreds of varieties, each promising unique benefits. The abundance of choice should be liberating, allowing you to find the perfect match for your taste and nutritional needs. Instead, many people find the experience overwhelming and anxiety-provoking. They spend excessive time comparing options, second-guess their decision, and wonder if they made the best choice. The paradox operates through several psychological mechanisms. Choice overload occurs when the cognitive effort required to evaluate options exceeds our mental capacity. As the number of alternatives increases, the difficulty of comparison grows exponentially. We have trouble processing all the relevant information and become paralyzed by indecision.
Escalation of expectations compounds the problem. When faced with many options, we naturally expect to find something perfect or nearly perfect among them. This raises our standards and makes us more likely to be disappointed with what we actually choose. With fewer options, we're more willing to accept good enough rather than demanding perfection. The opportunity cost problem intensifies with more choices. Every option we don't select represents a potential benefit we're giving up. With many alternatives, the combined opportunity cost of all foregone options can seem enormous, making any single choice feel inadequate. We become haunted by thoughts of what we might have gained from different decisions. Regret and second-guessing increase with the number of alternatives. When a decision doesn't work out perfectly, we can easily imagine how one of the many other options might have been better. With fewer choices, there's less basis for regret because there were fewer alternatives to consider. The paradox appears across many domains of life. Dating apps provide access to thousands of potential partners, but studies suggest this abundance can reduce commitment and satisfaction in relationships. People with more dating options report feeling less satisfied with their actual partners and more likely to continue searching for someone better. Educational choices present similar challenges. Students with many college majors, course selections, and extracurricular options often feel overwhelmed and uncertain about their decisions. The pressure to choose the optimal path can create anxiety and reduce satisfaction with whatever path they do select. Consumer research consistently demonstrates choice overload effects. Customers presented with large assortments of products are less likely to make purchases and less satisfied when they do buy something. Companies have learned to limit options in certain contexts, recognizing that too much choice can hurt sales and customer satisfaction. The paradox has implications for public policy and institutional design. Retirement plans with too many investment options see lower participation rates. Healthcare systems with numerous insurance options can overwhelm patients and lead to poor decisions. School choice programs sometimes create more anxiety than satisfaction for parents trying to select the best education for their children.
However, the paradox doesn't apply universally. The optimal number of choices depends on several factors, including the importance of the decision, the expertise of the decision maker, and the time available for choosing. Experts in a field often benefit from more options because they have the knowledge to evaluate alternatives effectively. Cultural differences also influence how choice affects satisfaction. Some research suggests that people from individualistic cultures are more susceptible to choice overload than those from collectivistic cultures, possibly because they place greater emphasis on personal responsibility for decisions. The paradox suggests several strategies for managing choice effectively. Satisficing rather than maximizing involves setting good enough standards and choosing the first option that meets them rather than searching exhaustively for the best possible alternative. This approach can reduce decision time and increase satisfaction. Choice architecture can help by organizing options in ways that make decision-making easier. Default options, recommended selections, and progressive disclosure of information can guide people through complex choice environments without overwhelming them. Some philosophers argue that the paradox reveals deeper truths about human nature and the good life. Perhaps the Western obsession with choice and individualism conflicts with psychological realities about how we actually make decisions and find satisfaction. Maybe some limitations on choice, whether imposed by culture, institutions, or personal commitment, actually enhance rather than restrict human flourishing. The paradox also raises questions about freedom and autonomy. If having more choices can make us less happy, what does this mean for political systems built on maximizing individual liberty? Should societies sometimes limit choices to promote well-being? Or does this threaten fundamental values about human dignity and self-determination? Understanding the paradox of choice has practical implications for personal decision-making. Recognizing when we have too many options can help us develop strategies for managing complex choices. This might involve deliberately limiting our alternatives, seeking advice from experts, or accepting that no choice will be perfect.
The birthday paradox. In a group of just 23 people, there's a greater than 50% chance that two people share the same birthday. This seems impossible since there are 365 days in a year and only 23 people. But the mathematics reveals a counterintuitive truth about probability that challenges our understanding of coincidence and randomness. Most people's initial reaction to this statement is disbelief. With 365 possible birthdays and only 23 people, it seems like the chances of a match should be tiny. Our intuition suggests we'd need much closer to 365 people before matches become likely. This makes the birthday paradox a perfect example of how mathematical reality can violate common sense. The key insight is that we're not asking about the probability that a specific person shares your birthday. Instead, we're asking about the probability that any two people in the group share a birthday. This seemingly small change in the question makes an enormous difference in the calculation. To understand why, consider how many possible pairs exist in a group of 23 people. The first person can be paired with any of the other 22 people. The second person can be paired with any of the remaining 21 people, and so on. The total number of possible pairs is 253. Each pair represents a chance for a birthday match, dramatically increasing the overall probability. The mathematics works by calculating the probability that no two people share a birthday, then subtracting from 1. For 23 people, the first person can have any birthday. The second person must have a different birthday, which happens with probability 364 over 365.
The third person must differ from both previous people, happening with probability 363 over 365. Continuing this process and multiplying all the probabilities gives approximately 0.493, meaning there's about a 50.7% chance of at least one match. The counterintuitive nature of this result reveals systematic biases in human probabilistic reasoning. We tend to underestimate the likelihood of coincidences and overestimate our ability to predict rare events. The birthday paradox demonstrates how poorly our intuitions serve us when dealing with combinatorial problems involving multiple comparisons. The paradox appears in many real-world contexts. In any moderate-sized gathering, shared birthdays are much more common than people expect. Classrooms, offices, and social groups regularly experience this coincidence, often to the amazement of participants who haven't considered the underlying mathematics. Similar effects occur with other types of matching. In a group of 14 people, there's a 50% chance that 2 people were born on the same day of the week. With just 6 people, there's about a 50% chance that 2 share the same astrological sign. These examples all demonstrate the same principle. When we're looking for any match among multiple possibilities, coincidences become much more likely than intuition suggests. The paradox has practical applications in computer science and cryptography. Hash functions, which convert data into shorter representations, must avoid collisions where different inputs produce the same output. The birthday paradox reveals that with a hash function producing n possible outputs, collisions become likely with approximately the square root of n inputs, much fewer than might be expected. Cryptographic systems must account for birthday attacks, where adversaries exploit the paradox to find collisions in hash functions or other cryptographic primitives. Security systems that ignore this mathematical reality can be vulnerable to attacks that succeed much sooner than designers anticipated. The paradox also illuminates broader questions about the nature of coincidence and meaning. When people experience seemingly remarkable coincidences, they often attribute special significance to them. The birthday paradox suggests that many coincidences are far more probable than they appear, occurring naturally due to the mathematical structure of probability rather than any deeper meaning.
However, the paradox doesn't eliminate the possibility of truly meaningful coincidences. It simply provides a framework for distinguishing between coincidences that are mathematically expected and those that are genuinely surprising. Understanding the baseline probability of various types of matches helps us calibrate our sense of what constitutes a remarkable occurrence. The paradox extends beyond birthdays to illuminate the frequency of shared experiences in any large population. In a city of millions, countless people will share unusual combinations of experiences, preferences, and characteristics. The paradox helps explain why social media platforms can often find surprisingly specific commonalities between users. Educational applications of the birthday paradox help students develop better intuitions about probability and statistics. Working through the calculation reveals how combinatorial thinking differs from linear reasoning. Students learn to identify situations where multiple comparisons dramatically increase the likelihood of matches. The paradox also connects to the broader phenomenon of the law of large numbers and the inevitability of rare events in large populations. While any specific rare event is unlikely, when you have many opportunities for rare events to occur, some of them almost certainly will. This principle helps explain everything from lottery winners to medical anomalies to seemingly prophetic dreams.
Variations of the birthday paradox explore different scenarios. How many people do you need before someone almost certainly shares your specific birthday? The answer is about 253 people for a 50% chance, and 1,179 people for a 99% chance. These numbers are much larger than the original paradox because we're now looking for a match with one specific date rather than any match among all possible pairs. The paradox reveals the importance of clearly defining probabilistic questions. Small changes in how we frame a problem can lead to dramatically different answers. This lesson extends far beyond birthday calculations to many areas where probabilistic reasoning is crucial, from medical diagnosis to risk assessment to scientific research. Understanding the birthday paradox can improve decision-making in uncertain situations. It teaches us to be suspicious of our intuitive probabilistic assessment and to carefully consider the mathematical structure of problems before drawing conclusions. This skepticism about intuitive probability assessment can prevent errors in everything from business planning to personal risk evaluation.
The paradox of analysis. If an analysis is correct, it seems trivial because it just restates what we already knew in different words. But if an analysis provides new information, it seems incorrect because it goes beyond what was contained in the original concept. This creates a dilemma. Correct analyses appear useless, while useful analyses appear incorrect. This paradox challenges our understanding of knowledge, meaning, and the nature of philosophical inquiry itself. It suggests that the entire enterprise of conceptual analysis, which forms a major part of philosophical methodology, faces a fundamental logical problem. The paradox reveals tensions between our desire for informative explanations and our demand for accuracy in definitions and analyses. Consider trying to analyze the concept of knowledge. Philosophers often propose that knowledge is justified true belief. If this analysis is correct, then it should capture exactly what we mean by knowledge, no more and no less. But if it captures exactly what we already meant, then the analysis tells us nothing new. We haven't gained any insight into the nature of knowledge, just restated our existing concept in different terminology. However, if the analysis does provide genuine insight, revealing something about knowledge that we didn't previously understand, then it seems to go beyond the original concept. This suggests the analysis is adding new content rather than just clarifying existing meaning. But then the analysis appears to be changing the subject rather than explaining our original concept. The paradox applies to many forms of intellectual inquiry beyond philosophy. Mathematical definitions face similar challenges. When we define a circle as the set of all points equidistant from a center, are we revealing something new about circles, or just restating what we already knew? If it's genuinely new information, how can we be sure we're still talking about the same concept?
Scientific explanation encounters related difficulties. When scientists explain that water is H2O, are they revealing the true nature of water or changing the subject from the familiar substance to a chemical formula? If they're revealing something genuinely new about water, how can the explanation be correct if it goes beyond what was originally meant by water? One response to the paradox argues that analyses can be informative even when correct, because they make explicit what was previously implicit in our understanding. We might have possessed the concept of knowledge without being clearly aware of all its components. Analysis doesn't add new content, but brings hidden structure into conscious awareness. This solution suggests that concepts can have internal complexity that we don't immediately recognize. Just as we can know how to ride a bicycle without being able to explain the physics involved, we can possess complex concepts without being explicitly aware of their logical structure. Analysis serves to reveal this hidden complexity. Another approach distinguishes between different types of meaning. The analysis might capture the reference or extension of a concept while providing new information about its sense or intention. Water and H2O refer to the same substance, but differ in how they present that substance to our understanding. The chemical analysis is both correct and informative because it provides a new way of thinking about the same thing. The paradox also raises questions about the relationship between concepts and the world. If analyses are supposed to capture objective features of reality rather than just our subjective understanding, then they can be both correct and informative. The analysis of water as H2O is correct because water really is H2O, and informative because it reveals objective features we didn't previously recognize. Some philosophers argue that the paradox rests on false assumptions about meaning and analysis. They contend that meaning is more flexible and context-dependent than the paradox assumes. Analyses don't need to capture fixed, eternal meanings, but can serve various purposes in different contexts.
From clarification to systematization to theoretical development. The pragmatist approach emphasizes the purposes served by analysis rather than its truth or falsity. Analyses are tools for achieving various intellectual goals, from resolving confusions to building theories to guiding research. Their value lies in their usefulness for these purposes, rather than in their ability to capture pre-existing meanings perfectly. Historical perspective reveals that the paradox reflects particular assumptions about language and meaning that developed in modern philosophy. Earlier thinkers were less concerned with sharp distinctions between analytic and synthetic truths, and more focused on the practical benefits of conceptual clarification and theoretical systematization. The paradox connects to broader questions about the nature of philosophical knowledge. If philosophy proceeds primarily through conceptual analysis, and if such analysis faces the difficulties revealed by the paradox, what kind of knowledge can philosophy provide? This has led some philosophers to abandon analysis in favor of other methods, while others have developed more sophisticated accounts of how analysis can be both correct and informative. Contemporary cognitive science provides new perspectives on the paradox by studying how concepts actually function in human thinking. Research suggests that concepts often have fuzzy boundaries, internal structure, and contextual variation that makes simple dichotomies between correct and incorrect analyses inappropriate. The paradox also appears in discussions of artificial intelligence and machine learning. When AI systems learn to recognize patterns or make predictions, are they discovering objective features of the world or creating useful but arbitrary categorizations? The success of machine learning suggests that analyses can be both accurate and informative, even if we don't fully understand how this is possible. Legal interpretation faces similar challenges when courts try to determine the meaning of constitutional provisions or statutory language. Judges must distinguish between legitimate interpretation that reveals original meaning and illegitimate judicial activism that imposes new meanings. The paradox of analysis helps illuminate why these distinctions are often controversial and difficult to maintain. The paradox ultimately reveals the complexity of our concepts of meaning, truth, and knowledge. It suggests that simple dichotomies between discovery and invention, or between description and creation, may be inadequate for understanding how analysis actually works in human intellectual life.
The Barber Paradox.
In a small town, there is a single barber who follows one simple rule. He shaves all and only those men in town who do not shave themselves. At first, the rule seems perfectly clear, but then the question is asked, who shaves the barber? If the barber shaves himself, then by his own rule, he must not shave himself, because he only shaves those who do not shave themselves. But if he does not shave himself, then he must shave himself, because he shaves all men who don't shave themselves. Either way, the rule collapses into contradiction. This simple scenario, posed by Bertrand Russell, isn't just a quirky riddle about barbers. It exposes a deep problem in self-referential systems, where a definition ends up applying to itself in a way that breaks the logic. The Barber Paradox is essentially a cousin of Russell's paradox in set theory, which asked whether a set of all sets that do not contain themselves could exist. The answer is no, because as soon as you try to decide whether that set contains itself, the same contradiction emerges. These kinds of paradoxes aren't just theoretical headaches. They shook the foundations of mathematics in the early 20th century. Before Russell, mathematics was thought to rest on clear, flawless logic. But this paradox revealed that even the most precise definitions could implode if they were allowed to refer back to themselves. This realization forced mathematicians to rebuild the very framework of their discipline, introducing new systems like type theory to avoid such circular traps. Beyond mathematics, the Barber Paradox serves as a cautionary tale about self-reference in law, language, and even artificial intelligence. A law that applies to all laws, including itself, creates the same circular tangle. A dictionary that defines dictionary using itself ends up looping without resolution. And in AI, systems that must evaluate their own decision-making can fall into similar self-referential pitfalls unless carefully designed. The Barber Paradox may sound like a trivial puzzle from a logic textbook, but its implications run deep. In any system where rules can apply to themselves, you risk a collapse of consistency. Sometimes, the only way to keep order is to carefully decide where self-reference must stop. Because once the rule turns its gaze inward, the structure that held it together can dissolve in an instant.
The Paradox of Omnipotence. Can an all-powerful being create a stone so heavy that even they cannot lift it? This question strikes at the very heart of what we mean by unlimited power. If they can create such a stone, then there exists something they cannot do: lift the stone. If they cannot create such a stone, then again there is something they cannot do: create the stone. Either way, their power appears limited. This paradox has puzzled theologians and philosophers for centuries because it seems to demonstrate that the concept of absolute omnipotence is logically impossible. The problem emerges from our attempt to apply logical reasoning to the concept of infinity. When we try to imagine unlimited power, we run into the boundaries of logic itself. Some philosophers have tried to resolve this by arguing that omnipotence doesn't mean the ability to do logically impossible things. They suggest that an omnipotent being can do anything that is logically possible, but creating logical contradictions falls outside this scope.
It's like asking whether God can create a square circle or make 2 plus 2 equal 5. These aren't limitations of power, but rather meaningless combinations of words that don't describe actual tasks. Others argue that the question itself is flawed because it attempts to trap omnipotence within human logic. They propose that truly unlimited power would transcend our understanding of possibility and impossibility entirely. From this perspective, an omnipotent being might indeed create a stone too heavy for them to lift, and then lift it anyway, because omnipotence operates beyond the constraints of logical consistency. The paradox becomes even more interesting when we consider what happens if the omnipotent being chooses to limit their own power. If they can voluntarily restrict their abilities, does that make them more powerful or less powerful? The ability to choose limitation might itself be seen as the ultimate expression of unlimited power. This paradox also reveals something profound about language and thought. We use words like omnipotent and unlimited as if they describe coherent concepts. But when we examine them closely, they seem to dissolve into contradiction. This suggests that human language and logic may be fundamentally inadequate tools for grasping certain types of concepts, particularly those involving infinity or absolute states.
The implications extend beyond theology into mathematics and physics. We encounter similar paradoxes when dealing with infinite sets, absolute zero temperature, or the concept of nothingness. In each case, our attempts to reason about absolute or infinite states lead us into logical tangles that challenge our basic assumptions about reality and reasoning. Modern philosophers have proposed various solutions, including the idea that omnipotence should be understood as maximal power consistent with logical coherence, or that the question rests on a category error that treats power as if it were a quantity that could be measured or compared. Yet none of these solutions feel entirely satisfying because they seem to diminish the very concept they aim to preserve. The paradox ultimately forces us to confront the limits of human reasoning and language. It suggests that some concepts may be so fundamental or so removed from ordinary experience that they cannot be captured adequately by logical analysis. Whether this represents a failure of logic or a glimpse of something beyond logic remains an open question.
The Paradox of Thrift. If everyone saves more money during an economic downturn, the economy should recover faster and everyone should be better off. However, when everyone saves simultaneously, consumer spending drops, businesses lose revenue, unemployment rises, and the economy gets worse. Individual virtuous behavior leads to collective disaster. This paradox, identified by economist John Maynard Keynes, reveals fundamental tensions between individual rationality and collective welfare. It shows how actions that are sensible and beneficial at the individual level can be harmful when everyone adopts them simultaneously. The paradox challenges simple notions of economic virtue and reveals the complex interdependencies within market systems. Consider what happens during a recession when people become worried about their financial security. The rational individual response is to reduce spending and increase savings. This provides a personal financial cushion and reduces individual risk. If only a few people behaved this way, it would have minimal economic impact while benefiting those individuals.
But when everyone responds rationally to the same economic signals, the collective behavior creates a downward spiral. Reduced consumer spending means businesses sell fewer products and services. Lower sales lead to reduced profits, layoffs, and business closures. Unemployment rises, making people even more anxious about their finances, leading to further reductions in spending and more saving. The paradox illustrates the fallacy of composition, where what's true for individuals isn't necessarily true for the group as a whole. Each person's spending is someone else's income. When everyone simultaneously reduces spending to increase their personal savings, everyone's income falls, making the savings goal harder to achieve and potentially pointless. The mathematics of the paradox emerge from the circular flow of money in the economy. Consumer spending becomes business revenue, which pays worker wages, which fund more consumer spending. When this cycle slows down, the total amount of money circulating through the economy decreases, reducing overall economic output and employment.
Keynes argued that this paradox justified government intervention during recessions. When private individuals and businesses are saving rather than spending, government can step in to maintain aggregate demand through increased public spending. This spending provides income to workers and businesses, preventing the downward spiral that occurs when everyone saves simultaneously. The paradox extends beyond personal saving to corporate behavior during economic downturns. Companies rationally reduce costs, lay off workers, and postpone investments to preserve cash and maintain profitability. However, when all companies behave this way simultaneously, they reduce the overall demand for goods and services, making the recession worse for everyone. Modern examples of the paradox appear during financial crises. The 2008 global financial crisis saw widespread increases in personal saving rates as people became concerned about job security and falling asset values. This behavioral shift contributed to the severity and duration of the recession by reducing consumer demand just when the economy needed it most. The paradox also appears in corporate cash hoarding during uncertain times. Companies build up large cash reserves as insurance against future difficulties. But when many companies simultaneously hold cash rather than investing it, the lack of business investment reduces economic growth and job creation, potentially creating the very conditions companies were trying to protect against. International versions of the paradox occur when multiple countries simultaneously pursue export-led growth strategies while reducing imports. Each country rationally tries to improve its trade balance, but if everyone exports more and imports less, global trade declines and all countries suffer reduced economic growth. The paradox reveals important insights about economic coordination problems. While markets efficiently coordinate many economic activities, they can fail to coordinate behavior during crises, when individual rationality conflicts with collective welfare. This market failure provides a theoretical justification for counter-cyclical government policies.
However, the paradox doesn't argue against saving in general. During periods of economic growth and full employment, increased saving provides resources for investment and future growth. The problem arises specifically during downturns when the economy has excess capacity and insufficient demand rather than insufficient resources for investment. The paradox also raises questions about economic education and financial advice. Personal finance experts typically recommend building emergency funds and reducing debt during uncertain times. This advice is sound for individuals, but if everyone follows it simultaneously during a recession, It can worsen the economic conditions that made the advice seem necessary. Some economists argue that the paradox is less relevant in modern economies with sophisticated financial systems and government stabilizers. Automatic stabilizers like unemployment insurance and progressive taxation can partially offset the effects of increased private saving. Central banks can also respond to deflationary pressures with monetary policy interventions. Critics of Keynesian economics argue that the paradox ignores the beneficial long-term effects of increased saving. Higher savings rates can lead to lower interest rates, increased investment, and higher economic growth over time. They contend that short-term economic disruption from increased saving is outweighed by long-term benefits. The paradox connects to broader questions about individual versus collective rationality in social systems. Similar dynamics appear in environmental protection, where individual rational behavior can lead to collective disasters like climate change or resource depletion. Understanding these coordination failures is crucial for designing effective policies and institutions.
The liar paradox.
Consider the simple statement: this statement is false. If the statement is true, then it's false, as it claims to be. If the statement is false, then it's true because it correctly describes itself as false. The statement cannot be consistently assigned a truth value without creating a contradiction. This paradox strikes at the foundations of logic and language. It shows that our normal concepts of truth and falsehood can generate contradictions when applied to self-referential statements. The paradox has appeared in various forms throughout history, from ancient Greek philosophers to modern logicians, and it continues to challenge our understanding of truth and meaning. The paradox becomes more vivid with concrete examples. Imagine a piece of paper with nothing written on it except the statement on the other side of this paper is true. You flip it over and find the statement on the other side of this paper is false. Each statement refers to the other, creating an endless loop where neither can be assigned a consistent truth value. Ancient versions include the Cretan paradox, where the Cretan philosopher Epimenides supposedly said all Cretans are liars. If he's telling the truth, then as a Cretan, he must be lying. If he's lying, then his statement might be false, meaning not all Cretans are liars, which could make his statement true. The paradox reveals how self-reference can create logical knots that resist untangling. The liar paradox isn't just a curiosity for philosophers. It creates serious problems for mathematical logic and computer science. Any logical system powerful enough to make statements about itself risks generating liar-type paradoxes. This discovery led to major developments in mathematics and logic in the early 20th century. Bertrand Russell discovered a similar paradox that shook the foundations of mathematics. Consider the set of all sets that do not contain themselves. Does this set contain itself? If it does, then it shouldn't according to its definition. If it doesn't, then it should. Russell's paradox showed that naive set theory, which most mathematics was based on, was inconsistent. These paradoxes led to the development of more careful approaches to logic and mathematics. Logicians created systems with restrictions on self-reference to avoid contradictions. Type theory distinguishes between different levels of statements, preventing statements from referring to themselves. Formal systems now include rules designed to block the construction of liar-type sentences. However, these solutions come with costs. Restricting self-reference limits the expressive power of logical systems. Some important mathematical concepts require forms of self-reference that risk creating paradoxes.
The challenge is to preserve enough expressive power for useful mathematics while avoiding contradictions. The paradox also raises deep questions about the nature of truth itself. If some statements cannot be assigned truth values without contradiction, what does this say about our concept of truth? Perhaps truth is more complex or limited than we typically assume. Some philosophers argue that the liar paradox shows that our ordinary notion of truth needs revision. One solution proposes a hierarchy of truth concepts. Instead of a single notion of truth, we might need multiple levels. Statements at one level can be evaluated for truth using concepts from higher levels, but cannot evaluate their own truth. This prevents self-referential loops while preserving the ability to talk about truth. Another approach embraces the contradiction. Paraconsistent logic allows contradictions to exist without making everything provable. In these systems, the liar sentence can be both true and false, without causing the entire logical system to collapse. This solution preserves classical reasoning in most cases, while handling paradoxical statements specially.
The paradox connects to broader questions about language and meaning. Self-referential statements appear throughout natural language, from "this sentence contains 5 words" to "I am now speaking." Most self-referential statements don't create paradoxes, so the liar paradox highlights specific features that generate problems. Modern computer science has encountered versions of the liar paradox in unexpected contexts. Self-modifying code, recursive programs, and artificial intelligence systems that reason about their own behavior can all generate liar-type situations. Understanding these paradoxes becomes practically important for designing reliable computational systems. The paradox also appears in everyday situations. Never say never is a self-contradictory command. All generalizations are false undermines itself. I'm not speaking cannot be true when spoken aloud. These examples show how self-reference can create logical problems even in casual conversation. Some philosophers argue that the liar paradox reveals fundamental limits to human reasoning and language. Perhaps there are truths that cannot be expressed without contradiction, or aspects of reality that resist capture in logical systems. The paradox might be pointing to the boundaries of what can be meaningfully said or thought.
The paradox of tolerance. A tolerant society should tolerate all viewpoints and ways of life. But what happens when it encounters intolerance? If a society tolerates intolerant ideas and movements, those forces might grow strong enough to destroy tolerance itself. But if the society becomes intolerant of intolerance, it violates its own principle of universal tolerance. Either choice seems to undermine tolerance. This paradox was most famously articulated by philosopher Karl Popper, who argued that unlimited tolerance must lead to the disappearance of tolerance. He observed that if we extend unlimited tolerance to those who are intolerant, the tolerant will be destroyed and tolerance with them. The paradox reveals a fundamental tension in liberal democratic societies between their commitment to freedom and their need for self-preservation. The paradox isn't just theoretical. History provides numerous examples of tolerant societies that welcomed intolerant movements, only to see those movements gain power and eliminate tolerance.
The rise of fascist movements in democratic Europe during the 1930s illustrates how tolerance can be weaponized against itself. Democratic societies extended freedom of speech and assembly to movements that explicitly aimed to destroy democracy. Consider the practical challenges this creates for modern democracies. Should hate speech be protected as free expression, even when it aims to silence others? Should political parties that want to eliminate democracy be allowed to participate in democratic elections? Should universities that value open inquiry provide platforms for speakers who oppose the principle of open inquiry itself? These questions force us to confront the limits of tolerance. The paradox becomes more complex when we consider that intolerance isn't always obvious or direct. Some forms of intolerance present themselves as merely alternative viewpoints deserving of respect. They might use the language of tolerance and freedom while working to undermine the foundations of tolerant society. This makes it difficult to distinguish between legitimate dissent and destructive intolerance. One proposed solution is to distinguish between tolerance for persons and tolerance for ideas. We can treat all people with dignity and respect while still opposing ideas that threaten the foundation of tolerance itself. This allows society to remain tolerant of individuals while maintaining the right to reject ideologies that would eliminate tolerance for others.
Another approach focuses on the difference between tolerance and acceptance. A tolerant society doesn't have to approve of or accept all behaviors and beliefs, only refrain from suppressing them unless they pose a direct threat to others' rights. This creates space for disapproval and criticism while maintaining the principle that diverse viewpoints should be allowed to exist. The procedural solution emphasizes protecting the institutions and processes that make tolerance possible rather than specific outcomes. As long as democratic institutions, free speech, and the rule of law remain intact, society can tolerate a wide range of viewpoints, but it must be intolerant of efforts to undermine these foundational institutions. Some philosophers argue for a contextual approach. The level of tolerance society should extend depends on circumstances. In times of stability, maximum tolerance might be appropriate. During periods of crisis or when facing existential threats, more restrictive approaches might be justified. This view sees tolerance as valuable but not absolute. The paradox also raises questions about who gets to decide what counts as intolerance worthy of suppression. If tolerant societies must sometimes be intolerant to preserve themselves, who makes these determinations? How do we prevent the cure from becoming worse than the disease, with authorities using the threat of intolerance to suppress legitimate dissent? Modern debates about cancel culture, deplatforming, and hate speech regulation often reflect this underlying paradox. Critics argue that attempts to combat intolerance have themselves become intolerant, creating a culture of censorship and ideological conformity. Supporters counter that tolerance requires active protection from those who would abuse it. The Internet age has intensified these dilemmas. Online platforms must decide what content to allow, balancing free expression against protecting users from harassment and harmful content. The global reach of these platforms means their decisions affect discourse in societies with very different traditions and laws regarding tolerance and free speech.
The paradox of tolerance ultimately forces us to recognize that tolerance isn't a simple principle, but a complex balancing act. Perfect tolerance might be impossible or even undesirable. Instead, tolerant societies must constantly negotiate the boundaries between openness and self-protection, between welcoming diversity and maintaining the foundations that make diversity possible.
The paradox of fiction. How can we have genuine emotions about things we know don't exist? When you watch a movie and feel afraid for the protagonist, or read a book and feel sad when a character dies, you are experiencing real emotions directed toward fictional entities. This seems impossible because emotions typically require beliefs about reality, yet we simultaneously know that fictional characters are not real. The paradox emerges from three seemingly obvious truths that cannot all be correct. First, we do have emotional responses to fictional characters and situations. Second, genuine emotions require corresponding beliefs about what is real or likely. Third, we do not believe that fictional characters actually exist. If all three statements are true, we face a logical contradiction. Consider what happens when you watch a horror movie. Your heart rate increases, you feel tension, you might even jump or cover your eyes. These are genuine physiological and emotional responses, not mere pretense. Yet throughout this experience, you never forget that you are watching actors perform a script. You don't call the police when you see a murder on screen, and you don't try to warn the characters about impending danger. Your rational mind maintains a clear distinction between fiction and reality. Some philosophers argue that we don't actually have genuine emotions toward fictional characters, but rather toward the idea or possibility they represent. When you feel sad about a character's death, you might actually be responding to the general tragedy of death or loss, with the fictional scenario serving as a prompt for these broader emotional responses. This explanation preserves the logical consistency but seems to diminish the specificity and intensity of our fictional emotional experiences. Another approach suggests that we temporarily suspend our disbelief so completely that we do, for brief moments, actually believe in the fictional world. During emotionally intense scenes, this theory argues we genuinely forget that we're experiencing fiction and respond as if the events were real. However, this explanation struggles with the fact that we can simultaneously feel emotions and remain aware of the fictional nature of what we're experiencing. The paradox becomes more complex when we consider that fictional emotions can be more intense than real ones. People often cry more at movies than at actual funerals, or feel more anger toward fictional villains than real criminals. This suggests that fiction might provide a safer space for emotional expression, allowing us to experience feelings that we suppress in real-life situations. Recent research in neuroscience reveals that our brains respond to fictional scenarios in ways remarkably similar to real experiences. Mirror neurons fire when we observe fictional characters, creating neural patterns associated with the emotions and actions we witness. This biological response occurs automatically, regardless of our conscious knowledge that the scene is fictional. The paradox also highlights the relationship between imagination and emotion. When we imagine hypothetical scenarios about our own lives, we often experience emotional responses. The transition from imagining personal scenarios to engaging with fictional scenarios might represent a continuum rather than a sharp distinction. Fiction might simply be a form of guided imagination that we share with others. Cultural variations in fictional emotional responses add another layer to the paradox. Different societies have varying expectations about appropriate emotional responses to fictional works, suggesting that these responses are not purely automatic but involve learned cultural patterns. This implies that our emotional engagement with fiction involves both biological predispositions and cultural conditioning. The paradox of fiction forces us to reconsider what we mean by genuine emotion and authentic experience. If fictional emotions feel real and produce real physiological effects, in what sense are they less genuine than emotions directed toward actual events? Perhaps the distinction between real and fictional emotions is less important than we typically assume.
The paradox of self-improvement. The harder you try to improve yourself, the more you reinforce the belief that you are not good enough as you are. This creates a psychological trap where the pursuit of betterment becomes evidence of inadequacy, potentially undermining the very goals you are trying to achieve. Self-improvement typically begins with the recognition that something about your current state is unsatisfactory. You want to be healthier, more productive, happier, or more successful. This recognition seems necessary to motivate change, but it also establishes a mindset of deficiency and inadequacy that can persist even as you make progress. The paradox becomes apparent in various self-help contexts. People who obsessively track their habits, optimize their routines, and constantly seek new techniques for improvement often report feeling more anxious and dissatisfied than before they began their improvement efforts. The focus on optimization can create a perfectionist mindset that makes any shortcoming feel like a failure. In meditation and mindfulness practices, similar paradoxes emerge. The act of trying to achieve a state of non-striving can become another form of striving. Attempting to let go of attachments can become an attachment to letting go. The more effort you put into being present and mindful, the more you might find yourself caught in mental loops about your meditation practice rather than experiencing the present moment. Psychology research reveals that excessive focus on self-improvement can lead to rumination, anxiety, and decreased well-being. People who constantly monitor their progress toward personal goals may develop hypervigilance about their shortcomings and become less able to experience satisfaction with their achievements. The paradox extends to social and cultural levels. Societies that place high emphasis on personal development and self-optimization often report higher levels of anxiety, depression, and dissatisfaction. The cultural message that everyone should be constantly improving themselves can create unrealistic expectations and chronic feelings of inadequacy. Social media amplifies these effects by providing constant exposure to others' apparent success and improvement. The curated highlights of other people's self-improvement journeys can make your own efforts seem inadequate by comparison, creating a competitive dynamic around personal growth that undermines its intrinsic benefits.
The paradox of knowledge. The more you learn, the more you realize how much you don't know. This creates a peculiar situation where increasing knowledge leads to increasing awareness of ignorance. Education, rather than providing certainty and confidence, often produces humility and uncertainty about what can be known. This paradox was recognized by ancient philosophers, most famously Socrates, who claimed that his wisdom consisted in knowing that he knew nothing. As people develop expertise in any field, they become increasingly aware of the complexity, nuance, and unresolved questions that exist within that domain. What initially seemed like straightforward facts reveal themselves to be provisional conclusions supported by incomplete evidence. The phenomenon appears clearly in academic progression. Undergraduate students often feel confident about their understanding of their chosen field, viewing the knowledge they acquire as definitive answers to important questions. Graduate students become increasingly uncertain as they discover the debates, contradictions, and gaps that exist in scholarly knowledge. By the time they reach advanced levels, they may feel less certain about fundamental questions than when they started. Scientific research exemplifies this paradox. Each answered question generates multiple new questions, and each new discovery reveals previously unknown areas of ignorance. The more sophisticated our instruments and methods become, the more complex and mysterious natural phenomena appear. Scientists often report that their research has made them more humble about the limits of human knowledge rather than more confident about what we understand. The Internet age has intensified this paradox by making vast amounts of information accessible to everyone. Rather than creating a more informed population, easy access to information has revealed the enormous scope of human knowledge and the impossibility of any individual mastering more than a tiny fraction of what is known. The awareness of how much exists to be learned can be overwhelming rather than empowering.
Specialized expertise creates its own version of the paradox. The more deeply someone studies a particular field, the more they realize how their knowledge is interconnected with other domains they don't understand. A climate scientist might become acutely aware of their limitations in economics, politics, psychology, and other fields that influence climate change, making them less confident about providing definitive policy recommendations. The paradox has psychological implications for learning and intellectual development. Students who recognize the paradox may become discouraged and lose motivation to continue learning. Others may become paralyzed by the awareness that any conclusion they reach is provisional and subject to revision. The recognition of ignorance can interfere with the confidence needed to make decisions and take action. Different philosophical traditions have responded to this paradox in various ways. Skeptical traditions embrace the uncertainty and argue that recognizing the limits of knowledge is itself a form of wisdom. Pragmatic approaches suggest that perfect knowledge is unnecessary for effective action, and that provisional conclusions are sufficient for most purposes. The paradox also reveals the social nature of knowledge. Individual humans can know very little, but human societies can accumulate and preserve vast amounts of knowledge across generations and specializations. This suggests that the appropriate response to the paradox might be humility about individual limitations, combined with appreciation for collective human intellectual achievement.
Modern information systems and artificial intelligence create new versions of the knowledge paradox. As our tools become more sophisticated at processing and analyzing information, we discover new layers of complexity in phenomena we thought we understood. Machine learning algorithms can identify patterns in data that humans cannot comprehend, raising questions about what it means to truly understand something. The paradox ultimately points to fundamental questions about the nature of knowledge, certainty, and wisdom. It suggests that intellectual maturity might involve learning to be comfortable with uncertainty and provisional conclusions rather than seeking absolute knowledge and definitive answers.